Hi, welcome to Algebra 2 Common Core. Today we're going to learn about the number e and the natural logarithm function, which is a unique form of the log function. Starting with the number e, we find out that e is a number that's very similar to pi. So we're going to use this lowercase letter e to represent this number. What do we know about the number e? First of all, like pi, e is irrational. Secondly, the value for e is approximately equal to 2.72. Now I'd like you to take a look at your graphing calculator. If you don't have it with you, pause your video right now and go ahead and get it. On your graphing calculator, you'll notice that there are two places where you can find e on the calculator. All the way to the left side, the third button from the bottom, on the key it says LN. We'll talk in a minute about what that LN stands for. But if you look right above the LN on your calculator, you'll see e to the x. So that means that we'll have to use the second button to get to that e. The other place where I can find e on my calculator is with the division button. So if I press second and then division, I'll actually be able to see quite a few of the digits for e. So pressing second and then division, e appears on the screen of my calculator. When you press enter, you should see the value 2.718281828. Even though it looks like a pattern there, this actually doesn't repeat indefinitely. Hence the reason that e is irrational. We're going to see a lot of this base e when we are doing exponential modeling, that is real-world application problems. Let's start first of all with the graph of e to the x. If I want to do the graph of e to the x, I've got four choices given to me, and I want to pick which one makes the most sense. First of all, I see that e is the base of the exponential function that we're talking about in this example. Now, that rules out choice number 1 because choice number 1 is clearly a parabola. It also rules out choice number 4. We're going to talk about that kind of function. It's called a cubic function, but we'll talk about that in a couple months. So we're down to either choices 2 or 3. 2 looks like exponential growth, 3 looks like exponential decay. Now if we go back and look, we say, oh yeah, e is actually equal to the number 2.718, etc. So when I look at my exponential graph, since e is a number greater than 1, I know that I must have exponential growth. So I'm going to pick choice number 2. What's my explanation for this? This is an exponential function, and of course it's an exponential function showing growth, so I'm going to say exponential growth. And the reason for that is because e is a number that is bigger than 1, and that's the base of the exponential. Now, as I said before, e is often involved in exponential modeling problems, both increasing and decreasing quantities. Even though e has a value greater than 1, sometimes we will be able to use e in decreasing models as well. So let's get right into an application problem with exercise number 2. It says a population of llamas on a tropical island can be modeled by the equation p equals 500 times e to the 0.035 t. Notice that t represents the number of years since the llamas were first introduced to the island. So the first question says how many llamas were initially introduced at time 0. We want to show the calculation for this, so let's not just put a number here, let's do the calculation. This one I don't even think requires our graphing calculator. We're going to say p is equal to 500 times e to the 0.035 times 0. Now, of course, that makes my exponent equal to 0, so I now have p is equal to 500 times e to the 0. Now, just like all other bases, like 2 or 3 or 10 for our exponential functions, anytime we're raising a base to a zero exponent, that part of my answer is 1. So that tells me that I really have 500 times 1, which of course means that my population at the beginning is 500 llamas. The next question, how many llamas will there be in 10 years? Well, that just means that we have to substitute 10 for the time because the time is being measured in years. So 500 e to the 0.035 times 10. Now I'm not going to do this piecemeal. I want to go directly to my calculator and enter the whole calculation. So when I do that, I'm entering 500. Now because e has an exponent, I'm going to use the E key on my calculator that's on the left side, the one that's right above the ln key. So I'm going to say second ln, which gives me the exponential, and then I'm going to raise it to the 0.035 times 10. Now once again, if you've got an older calculator that doesn't put everything in the exponent for you, make sure you put parentheses around that whole exponent. When I do that, I see that my answer turns out to be 709.5337. So because llamas can only be found in whole numbers of llamas, we're going to say there must be 710 llamas after 10 years. Now in part C, we want to do a calculation. We're going to use our calculator. So again, make sure you've got your calculator with you. And we want to find out how many years it will take to double the number of llamas. Since we started at t equals 0 with 500 llamas, we want to know how many years is it going to take to double. So our t is going to be our unknown when we have 1,000 llamas. Now, so far we've learned 2 different ways to solve this on our calculator. We can enter our equation for the population of llamas, so that's this equation back here, into our y1, and we could make a table of values, looking down the table until we see that we have at least 1,000 llamas. Our other option is to make a graph, so once again entering this function into y1, and then in y2 we would put 1,000 for the number of llamas. Now make sure that you adjust your window on your calculator. So when you do that, we have to make my y value go over 1,000. I made mine go to 1,200. For the x's, I'm talking about number of years, so I made my x start at 0 and go to about 30 to see how many years it's going to take to get 1,000 llamas. Go ahead and do the intersection point for that. Or if you're looking in your table of values, in either case we find out the intersection is at 19.8, but because it said how many years, my answer for this one is going to be 20 years. Now that's also the same answer that I see if I look at the table on my graphing calculator. For exercise number 3, we're still talking about a population, but this population is people. So let's look at our equation here. P of t is equal to 2,500 times E. So notice that we're not doing anything different when my base is E, other than how I'm entering this on my calculator. I'm not using a number like 2 or 3 or 10. Instead, I'm using the E key to write that base. So, since I need to find the population at several different times, I'm going to put this function into y1 because it's going to make it easier to solve for all 3 of these different years, and possibly even my final answer of finding when the population reaches 5,000. Let's just take notice, though, that the t is the number of years where t equals 0 represents the year 2000. So this is going to be important when we're calculating our time. So for the first part, for part A, it says let's find the population in 2002. Well, 2002 is 2 years after 2000, so I want to find the population at time 2. So we are substituting 2 in for time, so we're going to have 2500 e to the 0.0293 times 2. Now again, what I did to save some time on this one is enter my function into the y1, and then I actually looked at my table of values, and that allowed me to solve for all 3 years that I'm looking for. So if I look on the table, at time 2, my answer rounds, and again, make sure you're rounding to the nearest whole number because we're talking about people, so we don't want part of a person. So for 2002, we are ending up with 2,651 people. Keep going with the other years, so 2005 will be P of 5. So that's going to be the answer that we get when we do 2500 e to the 0.0293 times 5, or look at that value on my table, and on the table it turns out to be 2,894 people. Finish this part off with the year 2012, so that means I want P of 12. So 2,500 e to the 0.0293, this time times 12. And again, on the table of values, I don't even need to enter this equation into my calculator because I've already put it into y1, and I see that I've got 3,553 people. Clearly, the number of people is growing as the years progress. So it makes sense that I've got a base that is bigger than 1 because this is exponential growth. Now for part B, since I've already got my function in y1, and since I just need to know to the nearest year, I can just scroll down my table until I see 5,000 people. And I see that it takes 24 years in order to reach over 5,000 people. But make sure that you answer the question, because the question says during what year. So if it takes 24 years and my starting point was 2000, that means that the answer that I'm looking for is the year 2024. Continuing on to the back of our notes on page 12, if we go back and take a look at the graph from exercise number 1 for the function y equals e to the x, we clearly see that it's a function because it passes the vertical line test, but it's also a one-to-one function because it passes the horizontal line test. So any function that is one-to-one has an inverse. So let's take a look at what this inverse function is going to look like. Anytime I'm trying to find an inverse, that means that I'm going to take my original function y equals e to the x, and I'm going to reverse the x and the y. So I'm going to replace the y with an x and replace the x with a y. So I now have the equation x equals e to the y. Now we've gotten very good at converting between exponential form and logarithmic form. So when I do that, I see, remembering that the answer for a log is just the exponent, I'm going to start with the y equals log. My base, of course, is e, and the argument is x. So the inverse of the function y equals e to the x is this log function y equals log to the base e of x. Now this inverse is so important that it's actually given its own name. The inverse of y equals e to the x is called the natural log function. Sometimes the base of e is called the natural base of the exponential function. So the notation for this, we see above that this is just y equals log to the base e of x, but we also have its own notation. So its notation is y equals natural log. And we saw a minute ago how that key on our calculator said ln. ln actually stands for natural log. I believe it's because it's from the log with a natural base. That's why the L comes first and the N second. So whenever we want to refer to the inverse of e to the x, we will talk about the natural log function. Now, because natural log and e are inverses of each other, it's very interesting to see how natural log and e work with each other. So in exercise number 4, we're going to try to do these calculations without our graphing calculator. Looking at the first one, I've got natural log of e. If it helps you, you could rewrite this as log to the base e of e. Now that might make it a little bit easier to realize what this answer is. Think about our sprints. Whenever the base and the argument are equal to each other, that tells me that I must have an exponent of 1. So therefore the answer for the log is 1 because it's the exponent that e has to be raised to get e. Well, if the answer for log to the base e is 1, that's equivalent to saying the natural log of e. Looking at part B, the natural log of 1 just means log to the base e of 1. Now we all know that in order to get an answer of 1 for an exponential, the exponent, or the answer for the log, must be 0. So therefore the natural log of 1 is 0. These two properties are two of the most important properties for logs, and they're going to help us to solve some application problems as we continue through this unit. So let's try a couple more here. If I've got natural log of e to the 5th, that just means log to the base e of e to the 5th. So what do I want to raise the base of e to get e to the 5th? Well, the exponent has to be 5. So the answer for the log is just 5. And for part D, I could write this as log to the base e of the square root of e. So e would have to be raised to the 1/2 power to get it to be a radical e. So therefore the natural log of radical e is 1/2. Now the nice part about these natural logs is that everything we can do with regular logs, we can also do with natural logs. Natural logs are just a special case of the log function. It's the case where the base is e. So what we find out is that the natural log will follow all the rules that we have had for regular logs. So we'll be talking some more about that in class. So for exercise number 5, it says, which of the following is equivalent to the natural log of x cubed over e squared? So we notice that we have a quotient after our log. And again, it's okay that it's a natural log versus a log to any other base. So if I've got a quotient after a natural log, I'm just going to write it above here for sake of room. That means that I'm going to split this up into the natural log of the numerator, x cubed, minus the natural log of the denominator, e squared. So you'll recall that whenever we have a log of a quotient, we can expand that into the difference of the log of the numerator minus the log of the denominator. Now, of course, when we have exponents after a log, that means that we're going to be allowed to take those exponents down and they act as our coefficients in front of the log. So just like we did before with regular logs, this is going to be 3 times the natural log of x minus 2 times the natural log of e. Now if you look back to exercise 4, part A, you'll notice that we calculated the natural log of e, and we found out that the natural log of e was equal to 1. So this answer then is going to be 3 times the natural log of x minus 2 times 1, which according to our answers, our multiple choice answers, is choice number 2. Let's try exercise number 6. This time we've got the natural log of a product. So let's remember what happens when we have a log of a product. We're going to be able to expand that to the natural log of e to the fifth plus the natural log of x squared. So make sure you understand where these answers are coming from because of our rules of logs. Again, I'm going to see that I have exponents, so exponents become coefficients in front of the logs. So I now have 5 ln of e plus 2 ln of x. But once again, we see that special value of natural log of e, and we know that that has a value of 1. So we now have 5 times 1 plus 2 times the natural log of x, and that gives us our final answer of 5 plus 2 ln of x. Now, don't make the mistake of thinking that we can add the 5 and the 2 together, because the 2 is the coefficient in front of the natural log of x. So it's not possible to combine those two terms. Now, when you look at our multiple choice answers, though, you'll notice that because of the commutative property of addition, I can rearrange the order, and that gives me this answer, 2 natural log of x plus 5. For our last exercise tonight, we're again talking about a hot liquid that's cooling down. I hope you've noticed that we've had quite a few examples of these liquids that are cooling down to room temperature. The last lesson in this unit is called Newton's Law of Cooling, and it's going to be based on these hot things that cool off as they sit in room temperature. So we'll be looking at a lot more examples. For exercise number 7, a hot liquid is cooling in a room whose temperature is constant. Its temperature can be modeled using the exponential function given. T of m is equal to 101 e to the negative 0.03 m plus 67. So T stands for the temperature, it's measured in degrees Fahrenheit, and m stands for the number of minutes that it has been cooling off. So the question starts with, what was the initial temperature of the water at time 0? Number of minutes, 0. And it says, let's try this without our calculator. So we want to say T of 0 is equal to 101. Oops, made a mistake there. Not 100, 101 times e to the negative 0.03 times 0 for our minutes plus 67. So the exponential part of this function, any exponential raised to the 0 exponent, is just equal to 1. So that tells me that T of 0 is equal to 101 times 1 plus 67. So the temperature has to be 168 degrees Fahrenheit when this hot liquid starts cooling off. So that's at the beginning. For part B, what does it mean? How do you interpret the statement T of 60 equals 83.7? Take a minute to think about this. Pause the video, write down your explanation, and then come back and see if it matches mine. Hi, welcome back. I wrote down that after 60 minutes, the temperature of the liquid turned out to be 83.7 degrees. Now, of course, I'm not just going to take that on faith. I went to my calculator, I typed in this function into my y1, and I looked at my table of values at time 60. And it was correct that the temperature was 83.7 degrees. Good to know. Let's go to part C because we're going to use our calculator again. Using my calculator, let's determine when the temperature of the liquid will reach 100 degrees. Round to the nearest minute, so as long as we just have to round to the nearest minute, that tells me that yes, I can go ahead and use my table. I don't have to use the graph on the calculator. So when I did that, it turned out to be that m was equal to 37 minutes. Now, of course, if you prefer, or if I had to be more accurate than to the nearest minute, then I would put my function in y1, I would put my number of degrees, 100 degrees, in y2, I would adjust my window, and I would see where the two of them cross. So I would do the intersect feature. For the last part, on average, how many degrees are lost per minute over the interval from 10 to 30? So I hope you notice some important words in this question. On average. And then we're talking about a time interval from 10 to 30. I hope this makes you think of the average rate of change. So average rate of change is going to continue to come up throughout this course. This time we're applying average rate of change to an exponential function. So since my time interval goes from 10 to 30, I want to find the temperature at time 30 minus the temperature at time 10, and I want to divide by 30 minus 10. Now, since we want to round our final answer to the nearest tenth of a degree, it was accurate enough to look at our table of values. So on my table of values, I found that at time 30, the temperature was 108.06. As long as I've got one additional decimal place beyond what I want to round to, then I'm going to be okay. Minus t of 10, so that answer on my graphing calculator, and again, I just used my table. So minus 141.82, and I'm going to do that subtraction first, so I'm going to put that in parentheses, and then I'm going to divide by 20. Since I want my answer to the nearest tenth of a degree, I go ahead and do that calculation, and it comes up to be negative 1.6, and the rest of the decimals, 8, 8, dot, dot, dot. So rounding this to the nearest tenth of a degree, I am going to say that my final answer for this one, the average rate of change, negative 1.7. Now let's watch out for the units there. The numerator is, of course, measuring temperature, so that's in degrees. The denominator is measuring time, and my time was in terms of minutes. So this is negative 1.7 degrees per minute. Again, we notice that we had a negative answer because this function happened to show exponential decay. Look carefully back at your original function and see if you can see why it makes sense that this is exponential decay. Have a great night, folks, and we'll see you again in class. We'll do a lot more examples with natural logs and e's. Good night.